going around like this, so it moves to this point at a later point in the orbit. And if I measure what is the area enclosed by that approximate triangle, the law of areas tells us the following. So planets map out equal areas in equal time intervals as they go around the orbit. Okay, so that's the law of areas, and that's one way of thinking about it. Again, sort of just general sort of logical extrapolation of this. If you are on an eccentric orbit, what does that tell you about the relative speed of the motion when you're near the central object as compared to when you're far away from it?
When you're near it, it's a lot faster.
Right. So indeed, if you are close, let's say on the left side of that sketch, you're much closer to the central object. If you've got large eccentricity, you are moving faster as an orbiting planet in that case. So a simple corollary of this, when closer to the central mass, you are moving faster. So equal areas in equal time intervals. All right. Now, this is all sort of somewhat phenomenological. I'm not going to dwell on this, but I'm going to encourage you to look at the derivation, which is both in my notes, and I'm almost certain it'll be in our textbook, that actually casts this second law in a somewhat different way. And while I'm erasing the board here, I want you to think back to what you know about torque and angular momentum, and ask yourself, given that, to good approximation, our orbiting planets are always moving perpendicularly to the line that connects the planet with the central mass, what does that tell you to expect in terms of net torque acting on that orbiting planet? Yeah? Nice. Okay, good. So if you think about this, so we've got planet velocity is perpendicular to the direction of the gravitational force. That means there's no torque, and that means that angular momentum is conserved. Okay. So in fact, this turns out to be the more sort of Newtonian force law basis that underpins this is in fact a result of that relationship that angular momentum is conserved. And so we don't expect that to change as the planet is orbiting. So let me write this in two ways, which encapsulates both of these expressions. The area mapped out in a certain time interval is a constant, and this is the derivation that I'm not going to do in class, but for those of you that are interested, we can simply show that this is equal to the angular momentum divided by 2 over the mass. Okay? So you might like to look at this derivation, and it's just for your information. It's kind of nice to see how this comes around, because at this point you know how to do this. All right? So just look at it once through and just make sure you understand where this comes from, and we'll leave it at that. And then lastly is the, I think, law of periods. And once I've written that up, I'm just going to pause and ask if you have any questions. You can see I'm going fast. It's not because it's uninteresting, but it's more that it's sort of phenomenologically inspired rather than sort of directly derived from Newton's laws, which of course at this point you can probably do. So this is now the law of periods, and it tells us, it's a little bit of a mouthful, the square of the period of rotation is proportional to the cube major axis of the orbit. Okay, let me write this up in equation form. So here's the period squared is proportional to, is about to be my constant of proportionality. There's the cube of the semi-major radius. What is the constant of proportionality? It is that, okay? So this is the so-called law of periods, constant of proportionality, and so sometimes useful. Again, this is rather empirical rather than sort of looking at the underlying dynamics. So from a physicist's point of view, maybe not quite so interesting. So this is in general for elliptical orbits. Of course, when we've got zero eccentricity, this can become the radius for circular orbits. So let me pause there and ask if any questions. Again, I'm doing this relatively quickly because I kind of view it as touching base with astronomy in a sort of phenomenological way, but we're not really learning much new in terms of the underlying Newtonian dynamics. Yeah?
For the derivation, the empty mass of the orbit. Up above. Or GH.
This, correct. Make sure. Yes. Other questions? Yeah.
The second law, doesn't it just hold for like any ellipse, or is it actually just some special property or something?
That's what you mean by any ellipse. I mean, this thing's moving under a central force, right? So it's not geometry, it's dynamics. Yeah?
What's the other foci in the ellipse? What's the second like foci? Isn't like the gravity of the universe or something like that? Or like, do you know what I'm talking about? Okay, so like normally in like solar models, isn't the sun on one foci and then the other foci of the ellipse? Like, what's causing the planet to move in the orbit? You know?
Keep asking the question in a different way. So obviously what's causing it to move in its orbit is the Newtonian gravitational force, right?
Right, but what objects are acting on it, I guess? You know, like we have, like it's kind of like a centripetal force, but it's like not exactly, you know? Because it's like...
Okay, let's pass this and break it down a little bit, and I can see a couple of other questions. I mean, the only force in this two-object system is the gravitational force between them, right? So, yes, okay, so this thing is moving around in some trajectory. An ellipse is sort of like a more generalized version of a circle. Circles in ellipse with zero eccentricity. So it's moving around in some way. It's orbiting, rotating around that central mass. The only force acting on that planetary object is the gravitational force, right? So all that's happening in our Newtonian way of thinking is, since this thing has some initial velocity, in the absence of that central mass, it wants to move in a straight line, obviously. But now there's a mass there which has this gravitational force that provides a perpendicular acceleration, so it gets deviated slightly from that path, and of course this happens all the way around. So that's the only dynamics that's going on in this situation. I'm not sure, I'm not quite sure.
Here, I'll look it up.
All right, yeah.
Why doesn't it go around in a perfect circle? Like, what makes it go around?
So is there any reason why you feel it ought to always be circular, I guess?
It's like the little acceleration for like what it's actually the same way around.
Well, it's okay. Remember centripetal acceleration in the sense that we normally talk about it. It has to do directly with circular motion, right? But what is it? It's simply, we're talking about a force that's pointing in a certain direction and the corresponding acceleration. So I know we've spent a lot of time looking at perfectly circular orbits, but that's very much a special case. Again, all that is necessary to be here in this case is a gravitational force. And I guess you might ask the question, maybe how did it get to be in this situation and how did it start out? And that obviously has a lot to do with how dense clouds of gas coalesce and as planetary systems fall. And of course there's some initial angular momentum and so on and so forth. So there's no obvious reason why circular trajectories should be the norm. Yeah.
I was just going to say that it makes sense. It's all based on an initial condition, like
Right.
you said.
Right.
Every planet could be orbiting in a perfect circular orbit if it hadn't come into an interaction where it was like, for example, coming in a straight line, coming towards some massive object which gets sucked into an orbit around. And in that case, it makes sense that the orbit isn't circular because the force becomes stronger as you get closer to it. And so there's going to be some variation as your radius
Yeah,
changes.
so keep in mind, and maybe it's more a question of how do these systems form in the first place. It's a little bit off topic, but again, just keep in mind, a lot of people still study this as being an active area of research. How is it that large gas clouds, let's say from the early universe, under the influence of gravitational attraction, how is it that they coalesce, still maintaining angular momentum in the absence of external forces? And in general, you're going to get a rather complicated set of dynamics, okay? And in fact, if you look at the motion of planets in our own solar system, not only do none of them have perfectly circular orbits, but they're also not on the same plane, right? So kind of going at different planes as well. So it's a complicated dynamical system based on initial conditions. That's it. Yeah.
So is it correct to say that force Fg changes?
Sure. Remember, what does it depend on? The masses and the separation. So the masses are presumably constant to first order. In the case of the sun, not quite. But the masses are constant to first order. But the separation is constantly changing in the case of you've got an elliptical orbit. Okay. All right. I am going to try and do this quickly because I then want to show you some slides about non-Newtonian gravitation. Okay, let me come back to a slightly more Newtonian perspective on orbits, forgetting about Kepler's laws for just a moment. So let me come back to this middle chalkboard here. Okay, so we should expect for any system with central mass and an orbiting object, in general, we should expect it to be conserved. Why not? So we should expect that U plus K is a constant. All right, so we're going to do this just for circular orbits. It turns out it's true for elliptical orbits as well, but I'm just going to quickly talk about it for circular orbits. So what I can say is that U for an orbiting object is minus GMM over R. This is now the radius of the circular orbit. So that we know, what do we know, how can we find out what K is in general? So how do we find out what K is? Okay, so first off, let me remind you that I can relate the following. Now, the force is the mass times the acceleration. And now I am talking specifically about circular motion, so I'm perfectly justified to talk about a centripetal acceleration. So we know that force equals mass times acceleration for the circular motion. And that tells me then, just by making use of this, that I can write that K, obviously our standard non-relativistic kinetic energy, is just GMM over 2R. And then that tells us that the total energy, U plus K, is this plus this, and it is minus GMM over 2R, okay? So I'm just quickly make sure you understand what I did in a couple of seconds. Standard gravitational potential energy for radius little r. The kinetic energy, half mv squared, making use of F equals ma, I can write as plus GMM over 2r. And then the total energy is the sum of the above, and it turns out to be minus GMM over 2R. So let me just draw this quickly, so you can kind of get a little bit more of a visual feel of what I'm talking about here. So this is generally speaking energy. And so the U of R looks like this. K of R is half that value, but has now something that looks like, try and draw this obviously, half the other one. So this is K of R, and let me add some color to this for the total energy, which is now that. Okay. So this is E as a function of R. So again, the only thing I want to say about this is make sure you're not uncomfortable with the idea of this having a total negative energy. So, driven by the fact that our definition of gravitational potential energy is always negative, with our requirement that it goes to zero at infinite separation. Of course, kinetic energy is always positive, but it has half the magnitude of this. So that's kind of half the value of this for all values of R, and then when I add them together, I get the mirror image of this upper white one below the 0 point, which gives me my total energy. So don't be alarmed by the fact that that total energy curve appears to be negative. It's simply driven by the fact that we define gravitational potential energy to be zero at infinite separation. And that's pretty much all I want you to know about energy in orbits. This is done very much for circular orbits. It turns out that it's also true for elliptical orbits, in which case I'm allowed to replace R by A. Okay? So for elliptical, R goes over to A and it still works. Okay? All right, I know this is a little bit fast. Pretty much all I want to do about Newtonian gravitation, and see if there are any questions, and then I'm going to switch over and show you some slides, unusually just for sort of slightly more fun stuff about non-Newtonian gravitation. Yeah.
You said after K for G, big M, little m over R squared is equal to N G squared over R.
So this is just Newton's second law, F equals ma, force law. And I'm claiming that this is in a circular orbit, so this is simply mass times the acceleration. And since it's circular, I'm allowed to put my usual centripetal acceleration here. Yeah. Okay, so in the remaining 25 minutes or so, let's see if we can talk about some non-Newtonian. Yeah.
You're wondering, since energy is constant, why is it still a function of water?
So this is as a function of radius, right? So we're assuming this thing is moving around at a particular radius. So we're always kind of there for one particular orbit. So you're just taking different slices on this depending on what your particular R value is. And this is for circular motion. Okay, so talk a little bit about more interesting aspects of gravitation. I think I'm going to lower the light level here so you can see things a little more clearly. Okay. All right, so in particular, general relativity. So all of you have heard of this. We're just over the centennial anniversary of the introduction of general relativity in 1915. It's a radically different approach to understanding gravitation, as we already talked about on Tuesday. It thinks of gravitation or posits the idea that gravitation is more to do with the structure of space and more generally space-time, and that it's a lot more of an interesting concept, space-time namely, than we've kind of been thinking about up until this point. And so general relativity, I would say its primary idea is that gravitation is essentially a manifestation of space-time not being a rigid sort of, we tend to think of it, we kind of impose a somewhat human-centric idea of mapping out what space is by imagining these sort of Cartesian coordinates, sort of x, y, and z coordinates. General relativity throws that out the window and says we should instead think of space, and again more generally space-time, as something that is not fixed in that sense. It's not static, but is very much impacted and sort of dynamic based on the presence of mass and energy in that space-time. So this is the basis of general relativity. So a bit of background. So this is what we know already. Newtonian gravitation. Something I'm going to mention briefly, but I won't talk too much about. It's conceptually and maybe philosophically quite profound, but it has to do with two settings in which we've introduced the idea of mass at this point. So the one that's the second on this slide is the one that we kind of started out the semester with, and this is the idea of inertial mass. Mass as being some measure of an object's resistance to acceleration. And so in this sense, if I take F equals ma and recast it so that I divide through on both sides by acceleration, then I've got mass equals force over acceleration. And it's in this sense that we talk about an inertial mass. It's a measure of an object's resistance to being accelerated when a force is applied to it. So that's the idea of an inertial mass. We have, and I'm not sure what you'll think about this, in talking about Newton's gravitation law, which is the upper equation on here, we've introduced the mass of an object, and in both cases I'm talking about the lowercase m, which is really in the context specifically of that Newtonian gravitation force law. And there are a couple of ways of thinking about this. You can either think of that little m as being reactive to a gravitational force, or maybe even a gravitational field that's been established by the larger mass, big M. So you can think of it as being reactive in that sense, or of course you can think of little m as being the source of a gravitational force or a gravitational field acting on big M. So that's often described when people spend time worrying about these things as being a sort of active versus passive way in which little m serves as the definition of mass in this gravitational force expression. So we're totally used to thinking of m in these two contexts as being identical, but it turns out it's maybe not obvious that they are. And so over quite some time now, several centuries, people have asked the question and tried to answer the question, are inertial mass and gravitational mass for a particular object the same? Okay? So again, we're so used to overlooking this that we tend not to think about it, but there's no obvious or a priori reason why m in the upper equation ought to be equal to m in the lower equation. We're going to come back and talk about that in a while, because it turns out it was very much that question that drives or drove Einstein's thinking about general relativity, and eventually led to the conclusion that in fact gravitation and acceleration are kind of one and the same thing. Okay, so Newtonian gravitation obviously works generally pretty well. I'm going to run out of time for saying about interesting asides, but let me tell you something that I won't have time to talk much about, which is the following observation. If we look at rotations of objects on various scales in our universe, even within our own galaxy or even on smaller scales than that, and if we look at the rotations of objects around central masses, and in particular on the galactic scale, if we look at stars rotating about the galactic center, it turns out from everything that we can see that those rotations are inconsistent with Newtonian gravitation. And in fact, the rotational speeds of objects going around central masses do not seem to obey Newtonian gravitation. So this has been known about for about 50 years. You might ask the question, okay, does that mean Newtonian gravitation is wrong at large scales? That's a possibility, and one that a lot of people continue to explore, including people here in the department. The other possibility is that there's mass in something like our local galaxy that is there, but is totally, aside from its gravitational influence, it's totally invisible to us. And that's a much more popular explanation of these deviations in recent decades, that in fact our galaxy and all others, as far as we can tell, are filled with something called dark matter. So I'm not going to have time to talk much about this, but gravitationally this thing, dark matter, appears to exist. There's a lot of it. In most galaxies there's about 4 or 5 times more of it than there is regular matter that interacts with electromagnetic probes. So So dark matter seems to be a particularly sort of compelling explanation for these discrepancies with Newtonian gravitation at various scales in the universe. It's still not confirmed that this is real, though. Whatever dark matter is, we have yet to detect it directly, and there's a lot of effort going on, both here and at other research institutions, to try and detect this so-called dark matter directly. Anyway, that aside, other problems with Newtonian gravitation. There's no a priori understanding or explanation of why inertial mass and gravitational mass are the same thing. The second thing that you know already is, in a sense, there's no explanation either of how the information encoded in Newtonian gravitation gets transmitted. It's action at a distance. If a mass moves, how is it that an object that's under the influence of that mass knows that the original mass has moved? And in fact, there's no way to reconcile this with special relativity, which says there's a finite limit on how quickly information can get from one point to the other. That, of course, is the speed of light, and that's what we're going to talk about next week. More mundanely, and this is something that was known about 100 years ago, even more, is that in fact Newtonian gravitation is inconsistent with astrophysics and even the motions of planets in our own solar system. And so in particular, this is historically of interest, in the late 1800s, people were easily able to measure the planets in our solar system in great detail. And it became quite clear at that point, you can see here, well, it actually doesn't give a date, late 1800s. If you look, for example, at Mercury and its orbit around the Sun, the orbits are, of course, complicated. These are not two-object systems. Our solar system has a central sun, and either, depending on how you count, 8 or 9 orbiting large planets. And so there's a complex interaction between those objects. One of the phenomena associated with the fact that this is more complicated is that the orbits of these things undergo a sort of precession. So that ellipse that we've talked about is in fact itself rotating. That's what we call precession. And of course this was known about in the 19th century. But it turns out if you map this and measure it and try and reconcile it with Newtonian gravitation, it's slightly incorrect. Okay? I'm not going to go into the details any more than this, but this was known about in the late 1800s. All right. Whoa. I guess my translation from PowerPoint to PDF went awry. Okay, very cool. A little bit of a font issue here. Okay, what it's supposed to say down at the bottom is that the sun's gravity is not exactly 1 over r squared. It seems to be talking about you've got mail. So, anyway, possible explanations for why this is not correct. Of course, there are many you can come up with, and if you're a good scientist, you're going to propose various things and test them and see if you can rule some of them out. Turns out none of these things seems to be the answer. And so, in fact, we need something else. And the something else comes from general relativity. So there's a whole sort of series of threads that get us to general relativity, some of which we'll talk about briefly next week in the context of special relativity. But setting this in context both for next week when we talk about special relativity and the next semester when we talk about electromagnetism. Electromagnetism is the theory, classical theory that combines electrical and magnetic phenomena in this very beautiful framework. That's what we'll spend most of the spring talking about.